Hi, my name is Glenn Sizemore and I'm a technical marketing engineer in the Microsoft Business Unit here at NetApp. Today we're going to be discussing boot storms and what we've done at NetApp to virtually eliminate them. Like all server workloads, it is critically important that they be properly sized. But there's a conundrum in virtual machines that cause the under-provisioning that lead to the boot storm problem. And that conundrum is the fact that it is exponentially more expensive for you to weather that brief boot period than to sustain normal operations. And to show that, here we've just got a real simple workflow where we're going to start with 1,000 virtual machines. We're going to assume each VM is going to have a 20 gig VHD, and we're going to assume it's going to have 8 IOPS. That leaves us with a working set of 20 terabytes and 8,000 IOPS at nominal load. If we were to size for that, we could size for capacity. And that's obviously the starting point. And you'll notice that when we size for capacity, there is sufficient performance here to handle our nominal load. The problem is, if we were to start all 1,000 virtual machines, we would well exceed what's available in that bucket. That would cause exponential degradations in performance, and everyone on the controller would suffer. So how do we avoid that? Well, we could just buy more disks. We could buy sufficient spindles to have enough performance available in the pool so that we could handle that peak 8 a.m. boot storm event. The problem there being, as you can see, we are spending a tremendous amount of money to get there. Not to mention the power, space, and cooling cost of those disks that are only used for brief periods. With that in mind, we need to size this correctly, but we can't buy all those disks. So how do we solve this problem? At NetApp, we took a different approach. First of all, we start by right-sizing the environment. In reality, once we add in all our storage efficiency technologies, we don't need 20 terabytes of raw space. The max we're going to need is 10. We guarantee that. We're going to be 50% less. But then you get into the performance question and you say, well, wait a minute. Now you have even less spindles, so how are you possibly going to sustain? With Waffle and Data on Tap, we have a natively write-optimized operating system. So we don't actually need that many spindles to handle the write workload. But the read workload, you're right, we are drastically under-provisioned here. There is not nearly enough spindles to handle that 8 a.m. boot event. So how are we going to get around that? Enter our Flash Cache module. And as of Data on Tap 7.33, this Flash Cache module is deduplicated. It's dedupe aware. Now what that means is, if you get a 50% dedupe rate on your virtual machines, and as you can see here, we're pretty much saying you're going to get 50%. So that means that 50% of the blocks that are sitting on the disks are deduped. That also means that 50% of the blocks will be deduped when they get into cache. Now this causes what we call a cache amplification effect. Given my example workload of 20 terabytes, a 50% dedupe is going to give me an effective cache size of about 10 terabytes. Because we only ever have to store the first block. Every other block is going to stay on disk. This allows us to weather that 8 a.m. boot event. So how does this all work? The read IOP comes into the processor where we do a lookup in main memory. If we find that block is in main memory, then we have what we call a cache hit. And we're able to serve that I/O back out the back of the end of the controller in less than a nanosecond. Now, if we don't find that block in main memory, then we do a secondary lookup and we see if we have it in Flash Cache. If we have it in Flash Cache, we take a short trip across the PCI bus, or we grab the block, and then we serve the I/O back out. And we're able to get that done in less than a millisecond. Now, if we have to go to disk, the fastest possible response time we're going to be able to offer is somewhere between 3 and 4 milliseconds. And the reason for that is we've just got a lot of gear we've got to traverse here. Anything we can get from cache is going to be at least 10 times faster than anything we could possibly do on disks. So what does this mean? On a cold boot, the effect of booting 200 virtual machines is absolutely no different on a NetApp controller than booting a single VM. So as long as you have sufficient IOPS to boot a single VM in a reasonable amount of time, then you have sufficient IOPS to boot 200, 500, 1,000. So now let's see this in action. Here we have SCVMM connected to a single Hyper-V cluster with 6 Hyper-V hosts. On that cluster we have 230 virtual machines, 30 of which are up and running, so there is some load running. But now we're going to do something that would normally be considered very foolish and start all 200 VMs. Right away we see SCVMM starts to fire up the virtual machines as fast as Hyper-V will allow it. And if we look at the performance from the controller that these virtual machines are sitting on, you'll notice right away that the iSCSI protocol ops are just going to go straight through the roof as these virtual machines come up. And you'll also notice that the network sent in the I/O throughput is also going to climb. But notice how we only had the single spike of latency. That single 10 millisecond spike was the population of that cache. You know, the first handful of read requests had to go to disk. There was no way around it. Right? We were dealing with a cold cache situation. But once we got the first handful in cache, what happened then is we were able to progressively read from the disk before the bulk of the virtual machine load gets there. And you can see that by looking at the disk read compared to the network sent. You'll notice that we're reading 10 times less than we're sending. And that's that cache amplification effect. We only read the first virtual machine off disk. Every subsequent virtual machine after that is just booting straight off cache. And then the dip in the middle is as we max out our primary RAM and we start to actually populate that secondary RAM in our flash cache module. But once we get the flash cache module primed, you see the second spike is exponential to the first spike. You know, before we were doing 10,000 IOPS, and that was just with primary RAM and a handful of disks. But now that we've saturated all of that and we've actually moved into that flash cache module, you'll see that we're pushing 20,000 IOPS. Now, you'll also see the processor ebb and flow as those virtual machines come up because the processor is doing all the work right now. And at this point, all our VMs are started. And you'll see both the protocol ops and I/O throughput just absolutely nosedive because they're all up. To prove it, let's go ahead and connect to the very last VM that started, server 200. We'll open the console on this bad boy. And there it is, fully booted. 200 virtual machines in under 4 minutes. Not too bad. So the takeaway here is that by combining our storage efficiency technologies with our performance acceleration technology, you actually get a best of both worlds scenario. It's an and solution. There's no compromise here. You get to save on the power, on the space, on the cooling. You get to buy less disks and then still have the performance you need to weather that 8 a.m. boot storm. It's really fantastic stuff. I'd like to thank you for your time. I hope you enjoyed our presentation. And as always, to stay up to date with everything going on in the NetApp Microsoft ecosystem, head on over to blogs.netapp.com/msenviro.